Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's a pleasure to introduce Sam Geyer, an assistant professor at Tufts University in Boston. Sam got his bachelor's from Harvard in 1992 and his PhD from University of Texas in 2003. Sam's been doing a lot of really interesting work on program reliability, program analysis, and today he's going to be talking about VM introspection. So please welcome Sam.
Thanks a lot, Ben. All right, so I think that covers everything on the title slide there. Okay, so here's how I'm going to start this out here. So here's a question for you. How many techniques are there for handling buffer overflows and, I don't know, whatever other kinds of low-level memory errors, memory safety errors? I don't know. Actually, you know what? Don't actually throw out any numbers or anything.
Well, there's been 5 in the last year.
5 in the last year is probably good. Okay, so I made a list, I'm sure not exhaustive, but here's what I came up with. So, obviously there's type-safe languages, Java and C#. There's instrumentation for unsafe languages, so things like ccured. There's static analysis tools, so CSSV, and there's a paper from here, but I didn't have a nifty name for the system, at least that I couldn't see. Yeah, Montevier and so dynamic analysis tools, right? Robust runtime systems. I'm sure you're familiar with these. OS support. There's some hardware things. So, in my opinion, and you can argue with me about this, whether this is true, I think this is pretty much a solved problem, at least maybe from a research standpoint. And I think, so these techniques work really well. I mean, I think adoption of them, deployment of them is probably still a big problem. But there's a lot of really, really good ways to handle these kinds of bugs. All right, so, well, you can argue with me later about whether or not that's true. How about this? So how many techniques are there out there for sort of high-level memory errors? So here I'm talking about basically bugs in your data structures, right? And I guess I'll just qualify that and say, more importantly, how many are really effective at finding bugs in data structures? So, so here's a couple of things that are out there right now. There's a bunch of static analysis techniques, and they're cool because we can prove the absence of errors. Yay, that's good. And I'm definitely a believer. I think static analysis will get more powerful, and I hope, and here's Tom to rescue us. But right now it's still a really, really hard problem, right? So especially when you're talking about dynamic data structures, properties in the heap, where you want to build a very precise heap abstraction, but that's really expensive. Or I have an imprecise heap abstraction, and then I get a bunch of false positives. I can't really precisely check the properties I want to check, right? And oh wow, there was supposed to be a quote here, which I didn't actually put in, but I'll tell you. I'll just tell you what it was, more approximately. I meant to look it up. And programs have gotten a lot more difficult to analyze, right? So there's all these things in Java, dynamic class loading and reflection, bytecode rewriting, that just make this problem even more painful. And furthermore, the use of these application frameworks where programs are essentially wired together at runtime. And so even if you have some fancy whole program analysis, there's sort of a question of exactly what is the whole program. And the quote that was supposed to be here, that was not blah, blah, blah. I found this quote from a guy who writes a blog about web development in Java. And he basically felt like all Java applications should be wired together at runtime using some external specification, like an XML document that tells you how to assemble the application. So that, so this situation is tough. Yeah.
It's even worse if you look at JavaScript, right? Every time you load a web page, JavaScript is coming from many different sources, right? And it's not necessarily interacting a lot, but you don't know how it's interacting. Right?
Yeah,
So so every time you visit a web page, you're doing this basically.
Right, and obviously for sort of dynamic languages, I mean, I'm even talking about sort of semi-dynamic languages, but obviously it's even much harder for dynamic languages. All right, so okay, so that again, I hope that is ultimately the solution, but it seems like it's really tough still right now. Okay, so dynamic analysis, run your checks at runtime. And the good news about that is it's very precise because we're running on a concrete instance of the heap. We're not building an abstraction of the heap. We're looking at the actual heap. So in theory, we can have sort of no false positives, no false negatives. We just detect exactly the errors that occur. The problem here is that it's really slow. So there are some brute force approaches that are sort of in the 10x to maybe 100x slowdown to check program properties. So JML, and there's a bunch of these. There's, you can write a hand-coded checker for data structures that you run, and you have to remember to, so you can have bugs in that, and that's kind of a painful process. There's also been some interesting work more recently on making these checks incremental or sampling the properties to sort of control the cost, of the checks. So my viewpoint will be, I like the results right now for dynamic analysis, and what we'd like to do is fix the performance problem. And that's sort of the motivation for this work. Yeah?
So when would you stop? When would it be enough? I mean, are you looking to have something that you could run all the time with no overhead? Is that what you're looking at?
Well, the current state of the system, which obviously I'll show you, is almost zero overhead. It's something that could be run in deployment. And I'll talk about, there's sort of two branches of the future work. One which sort of continues with that idea, maybe not so much deployment, but maybe something like field testing, where you want the program to run at full speed in a real setting and record some extra information. Yeah, so that's kind of that's the goal. All right, so this work, GC Assertions, is work with my PhD student, Eddie Aftandelian. And the idea is we'll perform data structure checking during garbage collection. And so the advantage of this is we'll piggyback on existing computations that we're already paying the performance cost for. Right? So the collector is already traversing all the objects in the system during, let's say, a full heap collection. We'll just add a small amount of extra work to that, and we can collect a lot of interesting information almost for free. Right, so I'll show you in more detail what these properties are. But a lot of them are not surprisingly related to sort of reachability and a bunch of related properties like ownership, lifetime, shape. Yeah.
So these properties are not customizable? So as a user of your system, I get a predefined set of properties?
That is the current state of things is we looked at the system, we looked at garbage collection, we said, here are some properties we can easily check with very, very low overhead. And we're hoping to extend that. And I'll talk a little bit about that too. So some interesting things. Actually, the original motivation for this system was I actually just got frustrated myself with the fact that I had no way to really check if objects were being reclaimed by the garbage collector. And I was like, why can't I ask that question? Why can't I find out? And there was no real easy way to do that. So that was sort of the genesis of the project. And the general idea is, virtual machines have a lot of information about what's going on in the program, right? I mean, they're controlling the entire execution. And so, and we're looking at other facets of this, but the idea is provide some sort of introspective interface where the program can communicate with the virtual machine that's hosting it and ask questions about what's going on. And in many cases, it can answer those questions very easily because it's already collecting that information. So here's sort of the motivating example that we used in the paper. So there's a benchmark called JBB, standard Java benchmark. It's sort of been beaten to death on memory leaks, and so that was part of the reason we used it. Its behavior was well understood, and we wanted to see how our technique would apply to this. So it emulates this 3-tiered client-server system. It has a model of warehouses and customers and orders, and it sort of emulates this system. And it's got reasonably complex data structures, so it's sort of got database-like things in it. And here's a fragment of code, which I've simplified a little bit, but the idea is this fragment of code goes through a table of orders and flushes out all the orders from that table. So you get an iterator, and while we have more elements, remove orders from this order table, and at the end, set the order table to null. Right? So this is Java-ese for blow away the table. Right. Right. So what am I expecting to happen here? So I clear out the table and null out the reference, and GC will reclaim all of this stuff at the next garbage collection. Right. That's what I'm.
Can you go back to the previous slide?
Yeah.
You're changing order table inside the iteration?
Yeah, I know. I massaged the example a little bit. This actually doesn't remove the entry from the order table. It does something internal to the order itself. Yeah. Sorry, this was a much yuckier block of code that I know. I get some sort of what is it? Concurrent modification exception or something. Anyway, yeah. Sorry, I futzed with it a little bit. Right. So that doesn't happen, and the reason is, it turns out a customer object holds a reference to the last order made by that customer. And the customer objects stick around even as the order table is flushed. And so we have a memory leak. And it turns out, I mean, it's not a devastating leak because there's lots of orders and the customer only holds the last one. But there are other memory leaks in this program, which I'll describe a little bit. Okay, right. So the problem is it's actually a little deeper than just it's a memory leak, right? I had some unexpected structure sharing, right? The programmer who coded up the part that clears out the table didn't actually understand that customers would be pointing to the order, right? So there's kind of a specification problem there, right? And it's very hard to find those things without any special tools. Where is this order? Where's this extra reference coming from? And this is, one of the funny downsides of Java not having an explicit free is that, right, you can't actually ask about whether the order goes away, right? And I mean, it's definitely a mixed bag, right? In C, you could say free and be wrong, which would blow you up. But in Java, you're sort of all the way at the other end of the spectrum, right? You can't say free, you can't ask about it, you can't know it. Right, so our solution is to give programmers a way to express the expected behavior. So this object should be reclaimed to the next garbage collection. That's what I think is going to happen. And in its current form, this is styled after assertions that look like assert some property of an object. And you stick those things in your code.
Why don't you just provide a free statement to the Java program?
Yeah, well,
I mean, that would be, you can then interpret it the way you want, but it's like a way to express the intention.
Yeah. We've actually talked a lot about that. Is there a way to support free in some meaningful way as a hint or as a, right, like do the free if you can or or something like that. Yeah, we've talked about it. But this is focused on much more than just free, at least in this version. We could, for example, say, if I assert something is dead and it's not, go ahead and make it dead. Just make the assertion true is something you could do. OK, so let me first tell you a little bit about the sort of properties that we're offering, and then I'll describe how that's implemented in a garbage collector. So the categories that we have right now are lifetime, volume, and shape. And again, these are things focused on what can the garbage collector easily tell us without going into the guts of it. So, right, so here's the problem from the JBB example. An object that should be unreachable is not reclaimed. And again, there's no direct way to check this. Pretty difficult to discover by just program inspection. And the other thing to notice is only the programmer really knows what should happen there. The garbage collector just says, there's a reference here, so I'm assuming that's what you meant to happen. It doesn't have any other information to go on. So our solution to this is assertDead p, pass in a reference. And that's interpreted as star p, whatever p points to, should be reclaimed at the next collection. And there's a variant. We have a variant called assertReachDead, which says all objects reachable transitively from that object should be dead. So this whole data structure should go away. And if that's not true, then tell me about it. And obviously stop me if you have any questions about that. I'll talk a little bit about also what happens if the assertion is triggered. Yeah?
Can assertDead turn p into a null pointer? Otherwise, you could have a garbage collection between the assertDead and
Yes.
nulling, and bad thing will happen.
Yes, that is true. Right. So if a garbage collection were to recur right here, it would always be triggered. And what is the answer to that? That doesn't happen. We can't guarantee that doesn't happen, but I think we don't guarantee that doesn't happen, but we could. Right? We could make sure that we could just say, well, hold on to this information until the variable p is dead or something like that. Yeah, we could enforce that. We don't right now. Yeah.
So that's just something about whether p is live in the topmost stack frame, right? I mean,
Yeah.
Are there any rules in Java or anything about for all the other frames on the stack? When is p guaranteed to be dead?
In general, if there were references to this object in higher stack frames, then the assertion could certainly be triggered. Yeah. Yeah. So again, the idea here is you're the programmer. You know this.
I guess I'm wondering, does the compiler have the freedom to keep things live longer than the programmer might think that they're live?
Yeah, that's probably true. In other words, you could legitimately keep the variable p live certainly until the end of that method. That could certainly be legitimate. Yeah, that's a good question. So far, we haven't really seen any examples. We certainly haven't seen any kind of false negatives out of the system. I mean, the system we're using actually has pretty aggressive liveness analysis for the variables. So unless you actually use the variable later in the code, which clearly would not be a good assertion, it works out pretty well.
So I'm wondering if I'm asking the question that has been asked in different words before.
Yeah.
I'm still confused about the semantics of assert dead p.
Yep.
So at that point, p is referring to that object, right?
Yep.
So anything, if any program variable is referring to an object, it cannot be claimed.
Right.
It cannot be claimed by the garbage collector, right? Reclaimed by the garbage collector.
So so some of this is just an artifact of the system we're working in that I think a GC is not allowed to happen here. So there's specific GC points which are dictated by the compiler. So the compiler gathers sets of live variables, and then there are specific points where a GC can happen. And at least in this system, they only happen in at allocation sites, because that's the only place where you could need memory all of a sudden.
But there's a null of P somewhere, right? So I don't understand. Is it?
It's not a null of P.
There's no null of P?
Because at least, and I don't know a lot about.
If P points to some object, then it's going to maintain, right? I mean, it's going to. It's just that was the same question, right? So somehow P has to go away at some point.
Right. So what happens? And again, this is Jike's RVM. This is the system. I know how it works.
Right.
So what it's doing is it has a liveness analysis, so that at a point where you do a GC, it knows what the live variables are. So if P, it doesn't matter what value is sitting in P. If P is not a live variable later in the code, the garbage collector won't even look at it. It won't even consider it as one of the roots.
Okay. So the
So
assumption
the
is
garbage
that
collector is precise with respect to the liveness of the
you use
variables.
P because you know that P is dead.
Correct.
That's the only way you could do this, right? But let's say you didn't know that about your liveness analysis, right? Then you'd have this problem that somewhere you'd have to say P equals null, because you do need to kill P.
Yeah.
And then you have to assert that it's dead at some other point, and then you got a window where.
So I think then the solution would be that if you know that garbage collection will be done only at mallocs, then you have to make sure that after that assert dead P, and before the next malloc you do P gets null.
Right.
Right. And we could do, I mean, we could add just a little bit of compiler support for this, right? To just add a P equals null.
Well, I was going to say, you
We
can
could
also
do
say that one of the side effects with the assert is that it changes the range.
Yeah. So we'd have to do something a little, it just so happens we don't have to in our system, but yeah, this is actually, I think I had this discussion every single time I give this talk, so I should probably have something in here. It's like, but what if the GC happens right at the same time? Yeah. No.
You got a crowd of people think about transactions.
Yeah, totally. I know. Concurrency. What if interleavings of the?
Yeah, exactly.
So add the assertion and assertion run at the same time.
Okay. So here's another assertion, similar kind of idea. So if you have a server application, and what you want to happen is you sort of want to have a pool allocator kind of behavior, where I start servicing the connection. I may allocate all these different objects as part of the servicing the connection, and then at the end, when I'm done servicing it, I want to know that all the objects I created in between are gone. And this could be hard, right? How do I find the objects allocated servicing that connection? If I have a whole bunch of connections, which one is leaking objects? I don't know. So our solution to that is to give a region-like capability. So again, it's sort of in the same way that the same relationship between assert dead and free. This is sort of start region, assert all dead is like region allocation, except you're checking it instead of enforcing it. So you can say start region, do a bunch of stuff, assert all dead, checks to make sure all objects allocated in between are actually reclaimed. Yeah?
How do you do multiple regions then?
So right now we don't have multiple regions. Almost everything you'll see here has been tweaked for performance. So you can imagine nested regions where maybe you get an identifier that somehow says this is the region I care about at this point. You could imagine a much more sophisticated system.
So, but the semantics is that between two collections, you can see lots of start regions. The first start region is the one that matters. From that point on to the end of to the last assert. I mean, you can choose to ignore the issue of nesting, but you still have to give semantics to what happens, right?
Yeah, I think it's sort of the outermost.
It's the outermost.
Outermost start region, assert all dead.
Your program doesn't know that.
Yeah, the programmer doesn't know that. I mean, probably the reasonable thing to do here is to have a warning of some sort. But yeah, probably the better thing would be to have a more clear semantics about the nesting.
Right. And also, what if a start region is followed by a garbage collection without an assert all dead?
That's fine. We know how to handle that. So what's happening, if you have a garbage collection in the middle, then we don't actually check anything at that point. And any objects that are allocated here and die here, that's fine. I don't care about those.
Okay.
Yeah. Yeah, the nesting would be good to. Yeah, we're stealing. The implementation is we're stealing bits in the headers of objects, and to support sort of arbitrary nesting, we'd probably have to do something fancier with bits and have a lot more bits to work with there. So yeah, it's a little bit of a hack right now, but it does a lot just like this.
Is there real code that actually you can use this property for? And it would.
Application code?
Server apps, but I mean, the reality is that, just like with regions, if there's a single object that you allocate in there that lives past the lifetime of the region, then all of a sudden this doesn't, this gives you a false positive. Right?
Yeah.
So the question is, is that a common thing, or did you find code where it works correctly?
We didn't have good examples for this specific thing. I think we had examples that we sort of micro benchmarks that we made up, but it would be good to go in there. My sense is that you're right. There's going to be exceptions here, and there would be some good way to maybe say that, so that I can say this is actually going to produce a result of some sort, and it's okay if that lives past the. So we had a variant we explored that we never implemented that basically said, and this is just getting maybe even more ad hoc, but it was sort of start region, assert all dead except these things. Here are the things that are allowed to leave. Everything else should not leave the region. That might be more generally useful for this model. Yeah?
When you say any object allocated, does that mean system-wide?
Yeah.
Thread-wide?
Thread-wide, yes. You're right, thread, because it's...
So you could use this in like a multi-thread application?
You could. These are thread local allocation regions. And certainly we want to include system things because you're going to call into the libraries and allocate linked lists and hash tables and junk like that. Yeah. Yep. Okay, a couple more of these. So the Singleton pattern is one of these design patterns out there. So only one instance of this class should be live at any time. So it turns out, at least in Java, this is really hard to enforce. And it has to do with, you can serialize and unserialize things. There's lots of ways you can bypass the Singleton pattern, class loaders and stuff like that. So in our system, you can just say, assert the number of instances of this type is some number. And you just traverse the heap and tell you if there's more than one, which seems a lot easier than trying to fiddle with class loaders and such. Yeah, I think that's all I want to say about that. And we've thought also about variations that might be useful, like the number of instances matches some other system constraint, like the number of threads or the number of cores or something like that. There might be useful constants that you might want to check. We thought about having bytes, but then we weren't sure if that would be anything meaningful.
So these other semantics, you basically, I think the implication was that at some point in the future that all this stuff would be dead, as opposed to, it doesn't have to necessarily be dead right now.
Yeah.
So in this case, is the semantics that you're saying at some future point you will check that assertion?
Yeah.
Okay,
Not at some future point, at the next garbage collection.
Yeah, the next GC.
Yes.
So there is this kind of window, and
Yes.
you got to ask, I guess, is it unproductive to have, well, I mean, I don't know. It's an interesting question.
Yeah, I mean, this is and I sort of hit on this a little bit later so why don't I wait and I'll just describe, how does the system actually work, and then we can talk about what that means. So some other problems. So I want nodes in my tree. I've got a binary tree or something like that. Nodes in a tree should never have more than one incoming pointer. So I can use assertions like this. Assert unshared. So at most one other object points to this object. Or some extension, I can assert in degree or out degree of an object, sort of like Trishel's heap-MD stuff, but on a per instance basis here.
So
these
are all references that it checks, right? So
these are references, yeah.
If there's a garbage collection in the middle of you doing like a traversal algorithm, it can trigger that.
Yes.
Okay.
Yep. Yeah, in fact, one of the problems we found with assert unshared, and I'll show you on the next slide a sort of more useful variant of this. We found that iterators often violated these. So you would assume there's only one pointer to a node in the tree. Well, while someone's iterating over it, there's actually two. Yeah. So the most powerful of these assertions is designed mainly to solve problems like this, but it also solves that problem. So imagine you have a collection of objects, and there's some separate index of that collection, ordered in some other way or in a hash table, something like that. And the property I'd like is the index should never point to an object that's no longer in the original collection. And in particular, I don't want the index to keep objects alive when the collection is done with them. And this turns out to be a really common case of memory leaks, at least in Java programs. So you have a hash table, and the hash table just keeps getting bigger and bigger and bigger because you're clearing out the original containers, but you're forgetting to clear out that separate index of the objects. So for that problem, we have an ownership assertion. And the way to read this is there's some path from the roots of the garbage collection to star p, the object pointed to by p, that passes through Q. So this is a little different than traditional notions of ownership, which say all paths must pass through the owner to the ownee. We just require there's at least one. That way, you can have iterators and all these other references to the objects, but really the last reference to that object should be the owner. So slightly different definition. We found it was a lot more useful in practice than the sort of stricter definition. Okay, so those are the things we're offering right now. If you don't like it, we'll give you more really soon. So how does this work? So at coding time, you add assertions into your source code. So this is a programmer-driven technique. You have to go in and put these things in there, right, or it doesn't do anything. So you assert property on some object. At runtime, the inputs refer to specific instances of objects in the heap. And what the system does is it just saves the object along with the information about the property that you asserted. So nothing really happens when you execute the assertion itself. Right? I just squirrel the information away in some secret table inside the JVM.
So you talk about it as some of the programming would have, but you could have the notion of classes or whatever data structures that had these properties predefined.
Yeah.
Right? So here's a hash table and it maps this tree. And,
yep.
Yeah. So at some level, you could hide the fact that these assertions are being specified. Right?
Yeah. If there were sort of assemblies of interesting data structures,
or you
could
have
embed the rules in
a
there.
server type that that has this property that when it's done, all the stuff is for time.
Yeah, that's true. Like a connection type
Yeah.
that hides this protocol inside it. Yeah, that's true. We also have been talking with a couple of different people about some ways to do dynamic analysis or instrumentation to suggest a base set of assertions that might be true based on looking at what the program does. So maybe just something to get you started anyway. And then at GC time, we collect up all these assertions, and they're all checked at one time in one pass over the heap. So sort of the grungy details, we use the mark bit to test things like is shared, right? So we'll know in a regular GC traversal, if you encounter an object with its mark bit already set, there's some other pointer to it. So at that point, if we had asserted unshared, we would know that assertion was violated. Another thing we do is we actually change the traversal order in certain places in the garbage collection in order to discover specific information about reachability of objects. So let me show you an example.
You didn't have to introduce any extra state into the object header. You could just piggyback on top of whatever state there was.
Yeah. So we have in the worst case, the owned by assertion requires us to record the owner-ownee pairs. That's the most metadata we really ever have to store.
I see.
Everything else is done mostly with just a few extra bits in the header. And then things like counting the number of instances is really
How do
cheap.
you store that owner-only thing as an extra field or something?
No, that's an internal data structure to the JVM. So it has a table of what the owner-ownees are expected to be. So it has to look up that table. And that's sort of proportional to the number of owner-ownee pairs. So there might be declarative ways to sort of get that down. Like you could say, all of the objects of this type are owned by this object. But in general, it's hard to get a lot less than the list of assertions you need to check.
Actually, I'm not worried about that. I think that this is so cool that you should just make this completely full-fledged and customizable and let people specify whatever assertions make sense to them.
Yeah, we're trying to move to something that's more flexible. That's more like write your own assertions, and I'll describe that in just a couple of slides. So let me show you one kind of cool trick we did to get the owned by information. So if you can imagine, here's objects in the heap. Up at the top here, I have the roots. So these are objects referenced directly by the stack. Here's an owner object, and here's 3 objects that I said these objects are owned by that object. Right? So what we do here is we actually start GC scanning at the owner. Right? So now, once that completes, we've scanned everything. Now we know everything reachable from the owner. Right? So we could say, okay, good. These one's good. This one good. We check those off. Then we go back and do the regular scan. We're not going to visit any of this stuff again. And now we discover, here's an ownee. I should not discover any ownees when I perform this second full heap pass. So that tells me there's an error there. So again, we didn't have to collect a lot of additional information to get that behavior. Yeah?
You have to do this for every owner, right?
Yeah. So one caveat that I didn't tell you about is that in order to maintain the current performance guarantees, these sort of regions of ownership can't overlap. We can have multiple owners, but and we can detect if they overlap, but we can't get the right answer if they overlap. Yeah, we're trying to traverse everything exactly once. Yeah.
So how did you know that the owner was still live?
I don't. Yeah, actually, that's another good question that comes up every time. So here's what we do. So you can imagine if I just go ahead and mark this object and traverse this area, like this will never go away, right? Because I keep assuming this thing is live. So what we do is we start tracing here, but we don't actually mark that object. So what happens is, so this stuff will all be live, but when I start again at the roots, this may not be marked. So I'll have a drag of 1 GC potentially on this stuff. But the next time around, but then this will be reclaimed the next time around.
A cycle between the owner and the ownee.
A cycle between the owner and the ownee.
I mean, I guess that's an assertion violation. You're not supposed to do that.
Yeah, we'll
You'll have to check that.
I think
That's another one of those good questions.
yeah.
Have you detected?
I think we detect that. Let me think. So a cycle.
But you can detect it because the
We'll
owner
know
will
it.
be marked.
Yeah,
right?
the owner will
So
be marked.
at the end of this process. So that
No.
the
But what he's saying is, what if the reason the owner gets marked is only because the ownee?
Right, but you know that, right? Because you didn't mark it to begin with. You did a traversal.
We'll know we're in this initial pass, so we could detect that. But yeah, what do we do? I think we should just not ever mark the owner during this first pass. That's what we should. There, I might have to ask my student about, at that level of detail, what we're doing.
So if you relax the guarantees about when things get checked,
Yep.
you can handle these multiple owners also by just, one GC you handle this set of owners that are not on the next GC you handle these other sets. Right?
That's true.
That way you could be precise, but not as sort of timely. I guess.
Timely, yeah. That's really, and that's really the big trade-off here in this system, is the timeliness, the sort of completeness of the checking is something you trade for performance.
What is the typical time that elapses between two successive GCs on the applications you study?
In what kind of units? Like milliseconds or something?
A second?
I mean, I think it's probably milliseconds, I'm guessing.
So one question is, so if you don't do generational GC, okay,
Yeah.
then you have a certain GC rate. But then if you're doing some kind of partial GC,
Yeah.
will that work in that case? Will this work in that case?
Well, right. Okay, got that. So what we did, so we implemented this in a pure mark sweep collector because we wanted to visit the whole heap every time. There's a question. So if you do generational GC, there's certain things you can check even in the minor GC, but in general, you just defer checking of most properties until the full heap GC. So again, you just sort of stretch out the time in which you'll check these things. So, and clearly in this technique, you will miss transient errors, right? Something can happen, be broken in between GCs, and then maybe becomes garbage and goes away before you even look at it. That can definitely happen here. So the timeliness of it. When I was talking with Nikolai, he was suggesting a testing mode where what you do is every time you assert something, you just stop right there and force a full heap GC and check it. So you can sort of turn on that mode and say, give me the exact precise answer to this question every time I ask it. And obviously that's going to kill you performance-wise, but you'll get a much more precise answer.
Well, I mean, it's an interesting question about what the strategy is once you detect an error, right?
Yeah.
You haven't really talked much about that, and ultimately, if it's a deployed application and this error occurs, this assertion fails,
Yeah.
right? Sort of what do you do at that point?
Yeah.
And I think that kind of goes to the question of how timely is it, right?
Yeah. So let me blaze through because I want to talk about. Okay, so just really briefly for that JBB example, what we did is we put in assertReachDead on the orders and assertReachDead on the order table, and then ran the system. And so here's what we do now with that information. We just log it for our purposes and look at the results. So we're not doing anything like killing the program or anything like that. We just let the program continue running. But this is an interesting question. So our focus right now is on help the programmer find the bug, as opposed to handling it in some graceful way. So what we do is when an assertion is violated, we're able to provide the full path through the heap to the object that violates the assertion, which turns out to be really useful information. So for example, if an object is found to be live when you thought it would be dead, we give you all of the references that are keeping it alive. So that really has been extremely useful for finding the bugs. The implementation is kind of cool too. It's a very small change to the way object tracing occurs, and if you're familiar with the algorithm, what we do is we leave gray objects in the work list. That is, we leave objects in the work list that have been visited, but we haven't completed scanning all of their children. So when we detect a violation, we can just go backwards through the work list and report the list of gray objects. And that's the current path through the heap. So this is the assertion you get in that example. So it says an object asserted dead is still reachable. The type is order, and the path. And here I'm just giving you the types, because that's really the most useful information for the sort of programmer. But these correspond to actual object instances. So there's a potential to print more information there. So you can see, so we go through all these crazy B-tree data structures, blee, blah, blue, and down at the bottom here, you can see the customer still references the order. So then we go look at customer and figure out what's going on there. Some other things I'll kind of blaze through here. So we instrumented JBB with a lot more assertions than this, and we found a whole bunch of things. I think all but one of these had been previously known, but I think one that I thought was particularly interesting was we found an object that was being kept alive by an instance of a non-static nested class. So if you're familiar with this craziness in Java, if you have a nested class that's not declared static, it has a hidden pointer to an instance of the outer class. So what can happen is you can throw away all the references to that instance of the outer class, and the inner class instance can keep that object alive. And when we looked at the bug report, at first we didn't even understand what the bug was telling us. Like, what? Where? How is there a reference from this object? Anyway, so having the full path information was really useful. Anyway.
Were any of them actionable, or all of them?
We replicated finding some well-known memory leaks in that program. One of the things that's nice, though, is, because the assertion says exactly what the conditions are for the memory leak, you find out about it right away. You don't have to run the program and sort of wait for some data structure to get enormous and then go look at it. You find out the very first time something leaks, which is kind of nice. So performance, this is a graph of a whole bunch of benchmarks along the bottom and normalized execution. The red bars are the unmodified system. The blue bars here are just modifications we made to the JVM. We're not actually running any assertions here. So we had to make some modifications, including the changes to the tracing and bits in the header and junk like that. So there's a little bit of overhead just for adding the system, but it's not very high. And then we went through and instrumented, here's it's a funny graph my student made, the geometric mean of two things. I don't know. But so we instrumented JBB and DB with real assertions that corresponded to what we thought these programs should do. This would be hard to do for a lot of benchmarks, right? Go through and manually fix them. But you can see overheads very, very low, 1%, 2%, 3%. To give you an idea of what's going on here, in DB, we're checking about 15,000 assertions in every GC. And in JBB, now this is interesting. So we're checking about 400 in each GC, but we executed 31,000. And the reason those numbers are different is there are lots of assertions that we execute on objects that die before we even hit the next GC. So then we don't have to check them at all. They're already dead. But the point again is we can check a lot of things in one GC without imposing a lot of extra overhead.
So it looks like the overhead here is actually less than the base overhead that you showed in the previous slide?
It depends on the program.
Is
Yeah.
it totally negligible?
It depends on the program. It's basically negligible. What happens is the changes to the work list for printing out the path through the heap, I think those have the biggest impact because it causes the work list. The work list can get very big, and normally you would throw away all those gray objects. And so I think what's happening in some of these cases is we just have programs that end up with very, very long chains of gray objects just sitting in the work list, not really doing anything. But in general, and this is sort of what we were shooting for, was if I can just look at bits in the header that are already there, the performance impact should be basically nothing. Right. So, pros of the current system. It's fast and it's precise, within the confines of what I've given you. It's mostly non-invasive to the GC. So we did some tricks with the traversal, which hopefully are not creating cyclic garbage that kills us. I think it's not. And in particular for memory leaks, we were pretty happy with the results. It reports the errors quickly. It's very accurate. It's very informative. So the cons of this system, it's a pretty simple set of predicates, and they're not really composable in any way. You just say assert this or assert this. Those are your only choices. And of course, the properties are only checked at GC time. So we'll miss transient errors. And we also can't check a property at a specific time, right? So again, we're sort of trading the completeness of the system for performance. Right, and then the properties we're checking were really driven by what is the GC already doing, right? And we need to still compute that GC information, right? We can't perturb the collection order so much that we're not even computing correct reachability information for the objects. So we're sort of limited in what we can do there, right? So let me tell you a little bit about the sort of current and ongoing work to expand those capabilities. So this is work I'm doing with Yanis Smaragdakis and Neil Immerman at UMass. The idea is to develop a more full logic for describing these properties that we want to check. So the question is, assume we stick with this model of we're just going to check whatever we can do during a garbage collection. And the question is, what are the limits? How much stuff can you check just within a regular garbage collection? And so the idea here is to develop a language for these assertions, really a logic based on first order logic. And the goal will be any formula you can write in this logic can be checked in a single GC. Right? So it's sort of, you can think of it as linear time and the constant is 1. So pretty tough constraints from a complexity standpoint. So to give you some examples of, this is just stuff we're kicking around right now. So you could write a formula like this. There's no object X reachable from both object C and object D. Right? So you could write a formula of that form. And it turns out that particular formula can be checked in one GC pass. Right? I can scan from object C, mark all the objects, scan from object D. If I find any objects already marked, I know it's true, or I know it's false. There does exist an X that's reachable from both. Right, so we're looking at what combinations of predicates and quantifiers.
It's not obvious that that's composable in the sense that,
yeah,
because if you add that, if you had another one, A and B, A could overlap with C, and so having to.
Yeah.
It seems like you need, in some sense, you're limited by the number of colors you have with the marking.
Right.
You need a multicolor mark in some sense, or a way to have different distinction of colors, but to say, well, if it's any of these colors, then it's marked essentially.
Yeah, I don't know if it's. Yeah, I mean, colors is probably the right sort of. Right, you're sort of painting the heap and then asking about what the colors are. Yeah.
On top All right, you might have two assertions, each of which can be checked in a single pass, but
Yeah.
it cannot be both to get simultaneous pass.
That's right.
At least you have to prove you don't.
That's right. So I think, and this is ongoing, we're trying to figure out a model that captures when that's true and when it isn't. And right now we don't really know the answer. We know certain combinations that can and certain combinations that can't. And so it's still a process of sort of figuring out. Let me show you some other examples. So, here's something that's pretty easy and actually solves a problem that occurs in JSPs. So for all objects x, if x is reachable from an HTTP session object and it implements serializable. I want that to be true. It turns out that's one of the rules of JSPs. All objects reachable from the HTTP session must be serializable. And apparently this is a cause of wacky bugs. Right? It serializes.
As opposed to conjunction.
As I was saying it, I was thinking that. But implication. It should be an implication. Yeah. So that that'd be an example of just writing something more application specific by composing the predicates. Another really simple one. For all x, if x is a linked node, then x.next.previous equals x, right? Check that my linked list, my doubly linked list is properly formed. So the approach right now is take an assertion formula and compile it into a series of scans, which basically correspond to colors, I think. And then certain combinations of the quantifiers and operators result in non-overlapping regions. And again, this is still we don't fully know exactly what the capabilities and limitations there are. Yeah?
So there are really two limitations that you're working with. One is the question of what you can check in a scan. Another is a question of what valuable diagnostic information you can provide as a result of the scan. So assertReachDead, you can both assert and provide the path to the object. In this first example, you can assert that in one pass, but you can't provide both paths, the path through C and the path through D.
That's true.
That causes it to fail.
Yeah, that's a good point.
Deal with both of those questions.
Yeah, we could provide one of those paths. We could certainly identify X, right, as a witness, but we can't provide a...
Once you have a failed assertion, you can do a lot of extra work. So in theory, you could
true.
Just do another GC, essentially.
That's true.
So it kind of depends. I think the assumption is that it's very rare to have these assertions fail, right? If they fail all the time, then they're not all that good.
Right.
So you can do a lot of work.
Yeah, once the failure occurs.
Right.
That's true. Yeah, that's right. Just run it again and collect a lot more entry. That's a good idea. Yeah. So, and then finally, one more brief piece of ongoing work. So, sort of at the opposite end of the spectrum is this work on concurrent heap assertions. So this is work with Eran Yahav and Martin Vetchev at IBM. So a lot of checks just won't fit this model, no matter what you do. Right? So you might need special traversals that just can't easily be integrated into GC. And also, more importantly, if you want checks to be done at a specific point in the program, I don't want to wait for a GC. I need it to be checked right now. So the idea here is spawn off a separate thread to run the heap check, right? And the problem, of course, is the application keeps running, right? So it goes merrily modifying the heap. So you need some way to make sure that the checker sees whatever the heap looked like at the time it started performing the check. And the trick here is to harness the machinery of concurrent collection. So there's an algorithm called snapshot-at-the-beginning, which records the old values of references. So the checker can see that consistent view of the heap. Yeah.
It seems like, but the idea of having a consistent view from the point of view of one of these assertions across multiple threads or multiple concurrent threads, it's not even well defined, right? Because they're in some state. They're going to change. You don't when you sort of set the snapshot, you don't really know exactly what the state of all the different ones is. I guess you get a single state, so it's one consistent state. But
yes.
No, it is well defined actually. There's this notion of atomic snapshots.
Okay.
The idea is that you want you want the atomic snapshot to return some set of values which could be possible in some kind of a serialized execution, in which all the other operations you can pretend stopped, this guy executed, and returned some state that was stable.
Okay.
Yeah, I think that's the theory anyway.
Okay.
So just a point about that. I mean, I think
Let me just show you this.
The snapshot at the beginning is probably a lot stronger than for a lot of these assertions.
Oh yeah.
Right?
Yeah, so it saves everything, all changes, at least in the references to the heap. So it's probably overkill for this application.
But it's more or less just saying, hey, we already have it because it's concurrent
It's
GC.
an existing, yeah.
It's doing the snapshot at the beginning. I mean, I guess there's no additional cost because
Not above the concurrent. I mean, except in the sense that we are kicking off one of those snapshots every time we hit an assertion. So, and again, this is ongoing work is to figure out what to do, and there's a lot of these assertions. We can't just spawn off, thousands of these things. It's actually very hard to manage all the snapshots. But
So, I mean, it just doesn't seem. So to me, the way it seems is, in a lot of these cases. So, for instance, you have your region assertion before.
Yep.
Right. The region assertion is by nature per thread. Right. So there are probably some assertions that are just per thread anyway. There's a lot of things where there'll be data structures that are really per thread and so on.
Yep.
So it's only when you encounter something that's shared, and even then, only when it's shared and being mutated, this is a problem. So wouldn't it make sense to say, if this assertion fails, maybe next time I run this assertion, then I want to do the snapshot?
Well, maybe I'm not describing this. Maybe I'm not describing it correctly here. What's being made concurrent is just the check. The application itself doesn't have to be multi-threaded.
So actually, why do you want it to be concurrent? What are you
So
going
that
to
it's
get
cheap.
over it's cheaper?
Yeah, because I don't want to have to stop the program.
Oh, I see. So you're basically in a world where you're not working with stop the word garbage collection. This is
Right.
the only thing that you can do.
Well, it's even more than that. So imagine I have a check that's much more expensive. Like I want to know, intersecting regions of objects and, something that would make GC much, much slower. So instead of doing that, I'm going to run that check concurrently with the application. So the application keeps running, and I don't slow the application down.
But it might be doing some GCs as it keeps running, right? So you're a real GC that compete with your assertion check.
Well, right now it's still piggybacked on the GC. So the way it looks right now, and again, this is very much work in progress.
Right.
We have a concurrent garbage collector, which we've sort of piggybacked
Retrofit it, yeah.
GC assertions onto that. So now, and you might say, well, they were already so cheap. Why are you doing that? But now we can actually make them more expensive because now it doesn't matter. Now it's not going to slow the application down. Yeah.
Given that the two share a cache, it will slow the application down. If you start jumping all over the memory,
Yes.
cache degrades.
Yes. Yeah. Yeah. I mean, it's hard to. I don't think you can really do both without
It's okay. So
without
it's cool to
something.
do.
So, and in future work, we're kind of hoping to completely decouple, so to just use the machinery, but actually run completely arbitrary checks concurrently to the application. And there we would be sort of competing with the GC itself. Right now we're not, but we're looking at that as well.
Well, the flip side of that too is, I mean, if your regular GC is generational, then you could be doing these sort of global analyses in the background and not have to actually do a full GC, which can be pretty painful.
Right.
So.
Yep. And just, I love this. One of my favorite Conan O'Brien skits. So, in the distant, distant future of the year 2000, there's going to be a lot more of these virtual machines, all stacked up, running JavaScript on top of Java on top of hypervisors. And the question really is, the interactions are pretty complex. If things go wrong, what can we do about that? How can we ask about what's going on? And our idea is to provide an interface and actually ask those VMs what's going on. So thank you.
Any other questions?
Yeah, questions?
So give me an example of the craziest, most expensive assertion you would ever like to be checked. I mean, what would you, this is all a game of, you're trading off sort of expressiveness and obtrusiveness, right? So,
Right.
You'd like to, you're looking, especially with the language stuff, at some sort of sweet spot where you know that the queries will be discharged in a certain amount of time.
Right.
But, I mean, it seems, this has got to be limiting, right? So I'd like to hear, is it full specification of application? Or, I mean, what,
Yep, of course. No. It's, well, I think I can give you a couple of concrete examples. So one would be checking the real invariance of a data structure, like a red-black tree. Is it a properly formed red-black tree? Count the number of black nodes and look at the balance of the tree. And so people write code, like these rep-OK methods that crawl over the tree and make sure it's properly formed. And I think the idea with the concurrent checking is to just say, well, is there some way to just take that and run it concurrently? Because if you stop and do that every time you modify the red-black tree, you're going to die a horrible death.
So this sounds something like the stuff, like what Umutagar had done with his adaptive data structures. And wasn't there some follow-on work? There was actually a paper from Roz Bodek's group that was trying to look at specifically
incrementalize.
Exactly.
So what they do is they incrementalize the checks. They're still very expensive, though. I mean, if you could run them on a separate thread, on a separate core, you'd still win a lot.
Okay.
Yeah. The other one that I'm hoping to do is things like, you can have invariants like sort of set constraints. Everything in this container is a subset of the stuff in that container. And it's easy to express. It's really hard to check it.
It's interesting though, because part of the problem is, if you have a global heap and you've got a programmer reasoning about a local part of it, then they may not know what the global properties are. I mean, in some sense, I think one of the issues is you have to introduce this notion of what are the specified properties early in the design, and I think that goes back to the issue, like even saying, is this shared? One of the reasons that garbage collection was invented was so that people didn't have to ask that question.
Right.
Right. So you're sort of in a world where there are things that people know and want to express, but on the other hand, the more complex that becomes, the harder it is to actually build the system to maintain those constraints, right? So.
Yeah, that's true. I sort of viewed it kind of like you're describing, that by taking away the responsibility, you also took away the information.
Yeah.
And that, obviously.
The dead assertion is a good example, right? Where you don't really know if you're a programmer and you're dealing with your data structure and you don't know if somebody else is sharing it. I mean, it's trivial to add that assertion and find out.
Yeah.
I mean, so you can ask the question very cheaply.
Yeah.
And even if the answer is, oh yeah, there is this other guy, at least you've had a way to find it out without trying to read somebody else's code, basically.
Yeah.
So I think that's a really powerful tool. Okay, so any other questions? Thanks a lot.
Thank you.